In this tutorial, I'm going to walk you through a typical workflow of charge transport calculation using Perturbo. I'm going to use gallium arsenide as an example to demonstrate how to compute electron mobility as a function of temperature. Okay, now let's get started. So before for transport calculations, we need this EP1 file, EP1.h5 file. This file is generated in QE2 Perturbo calculation, and once generated, it could be used to it will be used in many calculations such as band structure, phonon dispersions, and transport ultrafast dynamics. So basically, this file contains all the information we need to perform those calculations. And this file is very convenient. So once generated, you can share with other people, with your collaborator, and transfer from one machine to another machine. And for this specific file, you can download from our website. We provide this file, so to following this tutorial, you don't need to generate this file by yourself. You can just download from our website. Okay, we can check the content of this file by using HDF5 tools, H5LS. So there are four different groups, and in a basic data group, it has all the basic information we need in a calculation, such as lattice constant, atomic position, and symmetry operations, and so on. And in the electron-phonon group, it contains the electronic Hamiltonian in a one-layer basis. In the force constant group, it contains the interatom force constant, which it will be used to compute phonon dispersion. And the EPH matrix one-layer group contains the electron-phonon matrix elements in a one-layer basis. So basically, it contains all the information we need to perform all kinds of calculation. Okay, now let's create a folder for this demo. Before the transport calculations, let's first create a soft link. So the reason I create a soft link instead of copying directly this file is because this file is quite huge. The size of this file is about 1.8 gigabyte. By creating soft link, you avoid create a lot of copy of this large file. So that will that will reduce your disk usage. It will save you a lot of disk space. Okay, so typically before transport calculations, I would do a band structure calculations, because by looking at the band structure, it will give me a better idea how to set up a energy window for this transport calculation. So let's first do a band structure calculation. To do that, first we need to generate an input file for this band structure calculations, and we provided a very convenient Python script to generate this input file for you. So -C, and we specify that we want to do a band structure calculations, and we provide the prefix and also the name of this input file. So this Python script has a lot of options. So if you want to check more, you can just -help. But here we just want the input file for band structure calculations. Let's open this file. So there are three parameters. So this one specify the files that so we need to provide the key path for this band structure calculations in this file. So I already prepared this file, so I just copy here. And if you look into this file, the format is very similar to quantum espresso band structure calculations. So each row specify a high symmetrical point along the K path. So here I'm just doing a band structure calculations of along L gamma X point, and the fourth column specify how many K points you want to sample along each segment. Okay, now we are ready to run the transport calculations. Since the band structure calculation is very quick, so we just run in serial. Okay, and the calculation finish very quick, and it generates this this file, and we can plot the band structure directly using this file. So we use the first and the fifth column. Okay, this is the band structure of gallium arsenide along L to gamma to X point. So now let's zoom in to the conduction band minima. As you can see that this is the L value, this is the gamma value, this is the X value. And since transport only electronic states in a gamma value contribute to transport, so later we will just set up energy window close to the conduction band minima. Okay, now to do transport calculations, we also need to generate an input file first. So we do that using this Python script. So now let's specify and tell the script that we want to do a transport calculation, and here perfect. Okay, let's check in this file. So here we need to specify the size of the K grid. We use 160 by 160 by 160. And we need to set the band range and the energy range. So the conduction band is the fifth band, and we only only the lowest conduction band is relevant for transport. So we specify the band range to 5 to 5, and we set the energy windows to from here to about 6.3. So that should be enough because it's more than 200 MeV above the conduction band minima. Okay, so since we specify our energy window, so before the actual transport calculations, we need to generate the K point that are within this energy range. So we need to do a setup calculation first before the actual calculations. Yeah, and also since we for transport calculations, we need to specify what is the temperature, what's the carrier concentrations or chemical potential. So we need to specify this information in this file. So here, each line specify temperature configuration. So, for example, the first column is the temperature, the second column is the chemical potential, and the third column is the carrier concentration. So usually either the second column or third column will be used because if you specify the carrier concentration, then the chemical potential is fixed. So the second column and the third column is not. They depend on each other. So, for example, if I want to do transport calculations at the 5 different temperature, but at the same carrier concentration, 10 to the 17th, then I will just specify the carrier concentration here, and then set this flag to true. That means in the setup calculations, the code will find the corresponding chemical potential here, and then update this file. Okay, so now let's run the setup calculation. The setup calculation is also very fast, so we just run it in serial. Okay, it's done. So you can see that by specifying the energy windows, the total number of key points is reduced to about 1,200, and the irreducible key point is only 90. And it also generates a lot of files. So the coordinate of all those irreducible key points is output to this file, and all the tetrahedrons and a full list of the key point is stored in this file. And we can check this KPT file. You can see that the first line specify all this information. You know, the size of the K grade and the number of tetrahedron and the K points within this energy window, and the number of irreducible K points. Then each line specify the coordinate of those irreducible K points. Also, let's check the this file. So now you can see that the flag is turned from T to false, and all the chemical potential is updated. So basically that if the temperature plus the chemical potentials will give this carrier concentration. So now in the actual transport calculations, then the code will simply read the first column and then the second column. Okay, now we are ready to run the actual transport calculations. Okay, let's go back to the input file and change the compute mode to chance. We also need to specify the maximum number of iterations, because now we are solving the Boltzmann transport equation iteratively, and then usually it's a good practice to specify the max number of iterations. And here, since this iterative approach converges pretty fast, so usually it will converge in less than 10 iterations. So the max number of iterations to set the max number of iterations to 50 is more than enough. And also you can also specify a threshold for this iterative process here. So usually the default value is okay, so you don't need to specify this parameter here. Okay. So yeah, that's we are ready to run actual transport calculations. But this since this transport calculation is usually quite expensive, we need to run it in parallel. So I prepared this simple script to run these calculations. So you can see here, here we use 4 MPI process, and each MPI process will span 5 OpenMP threads. So in this run, the code will use 20 CPUs in total. Okay, let's run a calculation. So first, it will find all the KP pairs and distribute nearly almost evenly among different processes. Then each MPI process will compute the electron-phonon matrix elements, and after they finish this calculation, they will output this electron-phonon matrix elements to disk in a format of HDF5. So after they finish the electron-phonon matrix elements, they will do the transport calculations, and you can see that the whole calculations finish in less than 30 seconds. So it's very efficient. And here you can see that the transport result is output in this file. The first data block is the conductivity for different energy and temperature configuration. The second block is the mobility, and the third block is the Seebeck coefficient and the Seebeck conductivity. So we can plot the electron mobility as a function directly using this file. For example, if I can do this, so if I use this file and use so index 1 means we are plotting a second data block. So you can see that this is the electron mobility as a function of temperature. We can also check the iterative process in this file. You can say for each temperature configurations, it will print out the iterative process, the conductivity computed in each iterations, and it will print out here. You can see that the iterative process usually converged in about 8 or 9 iterations. Okay, we can also check the transport distribution functions, which will give you an idea, what the energy range that contributed to transport. So this the TDF transport distribution function is output in this file. So we can plot, for example, now let's plot this TDF for 150 in the first temperature configuration. Okay, so it plots all the temperature configuration. If we just want to show the first one, we can just specify index 0. Okay, so this is the transport distributions for 150 Kelvin. So you can say that only electronic states within roughly below 6.2. So only those electronic states, only electronic states within this energy range is relevant for transport. So the energy windows we choose, which is below 6.3, so it's reasonable. Okay, you can also find that this kind of file is generated in this this. So this is the electron-phonon matrix element. For each process. Since we use a 4 MPI process, so there are 4 these files. So P1, P2, P3, P4 means this is the electron-phonon matrix element of those 4 MPI process. Now, the reason we the code output those files to disk is because next time if you want to restart the calculations or you want to do the calculations for different temperature configurations, you can just load this file and escape the calculations of electron-phonon matrix element. The main reason that we want to do that is because usually the calculations of electron-phonon matrix elements is the bottleneck. It will take a lot of time. The actual iteration process is actually very efficient. For example, if we now let's say we want to do with adding more energy configuration in the calculations. So let's add more energy configurations in this file. Say now we want to do 8 energy configurations, and here like a 75 to 25 and to 35. Okay, now we have 8 energy configuration, and we want to restart the calculation by loading those already computed electron-phonon matrix element. So we can do that simply by turn this load scatter EPH, set this to true. Then yeah, we are good to go. Okay, now let's run the calculation again. You can see that it will escape the calculations of electron-phonon matrix element, and the whole calculation finish in just less than three seconds. So if you remember that in the previous calculations that involve the calculation of electron-phonon matrix elements, it took about 30 seconds. But now, even though we have more temperature configurations, we open the whole calculation finish in just less than 3 seconds. So basically, by escaping the calculations of electron-phonon matrix element, the whole calculation just speed up by 10 times. So that's why it's very important, to restart the calculations if possible. Okay. And that's all for this tutorial. Thank you.